Howdy guys, this is our second video to talk about topic 1.2, the mole concept. We're just reviewing basically what the mole is. Now I caution you when you look at these because they're not your typical Chem 1 kind of problems. Some of them can be a little tricky if you don't understand the terminology. So we want to deduce the total number of atoms and molecules in, let's see, 1 mole of methane. Let's see. So it helps to know if we know what methane is. That is CH4. Remember, that was 1 carbon bonded to 4 different hydrogens, right? So in its molar mass is going to be given to you as 16. Now, they will show up in paper 1 like this, just to ease into and just make things easier for you. So if it says M equals a number, that means the molar mass. Now, if it says M, if it just says M, it should be 16 grams per mole. But if it says MR, then it should be just 16. Because MR is the relative molar mass. That's talking about relative to carbon 12, right? How many atoms are in carbon 12. But this one is talking about how many grams are in the mole. So there's a subtle difference, but you may be expected to know that. So that's enough of that. 1 molecule of methane, so is CH4. So it's going to have how many atoms do you see? 1, 2, 3, 4, 5. So 5 atoms. And it's going to be 1 molecule. Duh, because it said 1 molecule. Now, if it said 1 mole of methane, so that means we're going to multiply all of these by 6.02 times 10 to the 23rd, right? By Avogadro's number. So that is going to be 5 times Avogadro's number in A. And then 1 times Avogadro's number, right? So 5 times Avogadro's number is going to be 3.01 times 10 to the 24. And then this one's going to be 6.02 times 10 to the 23rd. And then for C, it says 1.605 grams per methane. So if you if your instinct right here was to just take grams and then convert grams into moles and do that, you could do that. But remember, if it's a multiple choice test, take a look at this. This is 1.6, and this is 16. So notice that this is 1/10 of that, right? So we'll just keep working it out, though. We have 16 right here, grams per moles, and then we'll convert moles into atoms. So that's going to be moles into molecules of CH4. Moles of CH4 to molecules of CH4. So that's going to be Avogadro's number in sub A. All right, so 1.605 divided by 16 times 6.02 times 10 to the 23rd is going to give us 6.02 or 6.03 times 10 to the 22 molecules of CH4, and then we would multiply that by 5 to give us times 5, and that's going to be 3.02 times 10 to the 23rd atoms in CH4. Okay, so you really have to kind of go through it and really see how those work. I hope that helped out. So let's look at question number 5. It asks how many atoms are present in 6.41 grams of sulfur dioxide, SO2. And check it out, the molar mass is provided for us for 64. So, question 5A, the molar mass is going to be 6.41 grams of sulfur dioxide. Let's just go ahead and convert SO2 to moles. And we'll put 64 right here. Divide by the molar mass. And it asks how many atoms are present. So we'll change moles into molecules. Moles of SO2 into molecules of SO2. And this is going to be Avogadro's number. So that tells you how many molecules of SO2 there are. But the question asks us for how many atoms there are. Well, you can see that there are actually 3 atoms right here. So what you would actually do is you would multiply by 3 right here to get 3 atoms. And that will bring you out to your answer, which is going to be 1.81 times 10 to the 23rd atoms. Now for B, we've got our xenon right here, and we have 262.6 grams of xenon, and our molar mass of xenon is 131.2. It doesn't take a genius to figure out that this number is double than that one. So, and luckily, xenon is just a singular atom. So that is going to end up being 2 moles of xenon, right? Or going to be 1.20 times 10 to the 24 molecule atoms. Okay, there's two moles of xenon atoms, which is an acceptable answer, or you could use 1.2 times 10 to the 24 atoms of xenon as well. Both of those are acceptable answers. Now, for this one, we have 3.603 grams of aspirin. So it's going to be C9H8O4. We'll change grams into moles. And I was helpful and looked up the molar mass for you. And so we will change our moles into molecules. And so there's Avogadro's number of molecules in 1 mole. And then we will multiply by our number of atoms. So 9 plus 8 plus 4 is going to be 21. Multiply by 21. So our final answer is going to bring us out to 2.53 times 10 to the 23rd atoms. Or you could write that as 0.42 moles of atoms. For question number 6, it asks us to deduce the number of nitrogen atoms. We have 5.00 times 10 to the minus 3 moles of ammonia, NH3. The molar mass is 17, but that's irrelevant at this point. What you would have to do is find out how many moles of NH3 there are, and then convert moles of NH3 into molecules of NH3, okay? Just by multiplying by Avogadro's number. And that will tell you how many molecules of NH3 there are. Then think how many, for every molecule of NH3 there is, how many atoms are in of nitrogen are in NH3. Well, there's 1. There's 1 nitrogen in every molecule of NH3. Now here, there are 2 nitrogens, and then here, there's only 1 nitrogen. So here, you would have to multiply by 2 because there's 2 nitrogens. Okay, so, but that's simply what it is. It's just going to be this number times Avogadro's number, and you will end up with 3.01 times 10 to the 21 atoms of nitrogen. So now we need to go back over empirical and molecular formulas as well. Remember that the empirical formula is going to be the most boiled down version, and is going to be the simplest version of a molecule. Now, many different molecules can share the same empirical formula. So examples would be if we had C3H8, and then we had C6H19. Well, they would both have the same empirical formula. The empirical formula of this one is going to be C3H8, right? Because it's the most boiled down version. I divided both of these by 2. That should be 19. It should be a 16. So C6H16, if you divide both of these by 2, you get that. So let's discuss an empirical molecular formulas, because that's wrapped into this topic as well. If you recall, an empirical formula is the simplest formula, and it is going to be the smallest portion, and then this one is not the smallest portion. So if something if we had a formula C3H8, let's say propane, and we had C6H16, and then we had C12H32. Well, all of these all have the same empirical formula, because you could break this one down. You could divide these two subscripts by 2 and break it down into C3H8, or you could break this one down also into C3H8. So they all have the same empirical formula. This one is a molecular formula and an empirical formula all at the same time. So we can derive them from these percentages that we get. Now, the way we get that is we put them into a combustion chamber, and then they ignite, and we're able to pull off CO2. We're able to pull off water, and then we're able to pull off CO2, and we're able to pull off water. We know that the CO2 came from the carbon, and we know that the hydrogen came from the water. So once we know those two things, we can deduce how much oxygen there is. So very frequently, it'll be in an organic molecule like this one. So aspirin contains 60% carbon, 4.48% hydrogen, and 35.52% oxygen. It has a molar mass of 180.17 grams per mole. We want to determine the empirical and molecular formula for that. So what we're going to do is we're going to assume a 100-gram sample. Now, what I mean by that is we're just going to say that 60% is going to be 60 grams, okay? And then 60 grams of carbon. And then we're going to have 4.48 grams of hydrogen. And we're going to have 35.52 grams of oxygen, okay? Then what we should do is we should convert them into moles. So essentially, I'm going to divide by its molar mass, and I'll show you the short way in a second. So grams per mole, we're going to divide by the molar mass here, and we're going to divide by the molar mass here. The molar mass of hydrogen is going to be 1, and then the molar mass of oxygen. Molar mass of oxygen is 16. And so that should give us 3 numbers again. And we end up with 16 divided by 12 is going to be 5. And then 4.48. And then 35.52 divided by 16 is going to be 2.22. So we end up with these three numbers. They're in the appropriate ratios, but they are not great numbers. So so we're, but what I mean by that is we could write the formula like this. Okay, but we don't want decimal places there, so we want to divide them all by the lowest number. Okay, that's the easiest trick. And when we do that, 5 divided by 2.22 is approximately 2.25. And then 4.48 divided by 2.22 is approximately 2. And this is going to be 1. Now, again, they're still not in whole numbers. So what are we going to do? We have to, we should probably multiply all three of these by the same number to try to get them that way. Because if we see this as a fraction, if we see this as 5/4 instead, and 4/4, and then, then it might work. So if we actually multiply this by 4, multiply this by 4, and multiply this by 4, then we end up with carbon's represented as a 9, and then hydrogen is an 8, and then oxygen is 4. So I end up with C9H8O4. Okay, very cool. Now for number 5, oh wait, that's its empirical formula. Now it gives us the molar mass here, which is 180, right? 0.17. So that means that we need to find this mass right here, the mass of this one, to see if it matches this one or how close it matches. So 9 times 12 plus 8 times 1 plus 4 times 16 is going to be 180. Okay, pretty darn close to this one, right? So if it's the same, then that means that the empirical formula and equals the molecular formula. It's the same thing. Okay, so this is the empirical and the molecular formula. Okay, so for number 5, an easier way to do this is it shows us that an organic compound has a molar mass less than 100 grams per mole. The percentage composition by mass of this compound is 71.38% carbon, 9.6% hydrogen, and the remainder being oxygen. So 71.38 grams of carbon. We have 9.60 grams of hydrogen, and the rest is oxygen. So this all has to add up to 100%. So I'm going to take 100, I'm going to subtract it by 71.38, and I'm going to subtract it by 9.6. I'm going to get 19.02 grams. So now that all adds up to 100. Hopefully that made sense. Now, once that's done, what you should simply do, again, is just divide it by its molar mass. Again, that's going to be 12. Carbon's 12. Hydrogen is 1. Oxygen is 16. And we'll get 3 numbers. It's going to be 5.95. 9.6 divided by, I do that all the time. 9.60. And then 19.02 divided by 16 is going to be 1.19. So again, not in the right ratios. So let's divide by the lowest number. 1.19, 1.19, 1.19. This is going to be 5. That's helpful. 9.6 divided by 1.19. This is going to be about 8, approximately 8. And then this is going to be 1. Oh, so good. I didn't have to do any of that extra stuff like I had to do here. I didn't have to multiply by another number. Usually that works out that way. Every now and then you have to add in that extra step. So I end up with C5H8O as my empirical formula. Now it asked me to find the molecular formula, and it said that the molar mass was less than 100 grams per mole. So why don't I just go ahead and see if I can figure out what this is. Let's see what the mass of this is. So 5 times 12 plus 8 times 1 plus 16 ends up being 84 grams per mole. So if I can't do anything else, because if I ended up blowing this up and blowing this up, all the subscripts up by 2, and if let's say I end up making C10H16O2, the molar mass would be greater than 100, so that can't work. All right, so it has to be this one. This one has to be the molecular formula as well. Okay. Now the last question is very good because it goes over what we did in our lab. This is actually a required lab, so this will show up somewhere on the test, probably somewhere. So it says that a piece of magnesium with a mass of 5.867 grams was heated in a crucible, which was open to the air. After the magnesium had combusted and allowed to cool down, the product was found to have a mass of 8.956 grams. 1, determine the empirical formula of the magnesium oxide formed, and then 2, the actual empirical formula of the magnesium oxide is MgO. Suggest 3 possible reasons why you got the wrong answer. So it says that we have 5.867 grams of magnesium. And if you remember, this is whenever we had the crucible right here, and we had our little Bunsen burner, and it shot out a flame, right? We had to heat it, and then we had our magnesium sample in here. We covered it with the crucible to try to prevent air to get into it, right? Do you remember doing that? I hope you did. And we measured it before and after. It took a long process, but it was a very good lab. So we started with this many grams of magnesium, and then at the end, we ended up with 8.956 grams of what we suspect to be magnesium oxide. Now we're trying to determine this formula, so we don't exactly know the subscripts right here. Now what this leads you to determine is that if we subtract these two, we end up determining the mass of oxygen. So this number minus this number is going to give us 3.089 grams of oxygen. That's helpful because now if we just take 5.867 grams of magnesium, and if we have 3.089 grams of oxygen, if we divide both of those by their molar masses, magnesium is 24.3, and then oxygen is 16. We end up with 0.241, and then 0.193. Now, these are now in ratio with each other, and that's what we want to see. But we want to get them in a prettier ratio, so we divide by the lowest number, 0.193. 0.193, and then we end up with approximately 1.25, approximately 1. And then this one is 1. So now we again we end up with this weird number that's not exactly a whole number yet. So let's make it a whole number. The easiest way to do that is multiply it by 4 and multiply this one by 4. So that magnesium's representative is a 5 and that oxygen's is a 4. So our empirical formula is going to be Mg5O4. Now that's not what we should have gotten. We should have gotten MgO. Okay? So we wanted to suggest 3 possible errors for that. Well, if you remember in our lab procedure, we ended up heating it up and then cooling it down and then heating it up again. That's because we were trying to get rid of nitrogen, right? So possible nitrogen contamination from the air that formed MgN. That would be Mg3N2, right? Or let's say not enough product. Not all reactants. Not all reactants reacted. Maybe the crucible participated in the reaction, so it, or the crucible was not inert. Maybe the magnesium wasn't pure. Or maybe some of the product escaped. Okay, so lots of good things that could come from this, lots of possible errors. Hey, there's 5 right here, but you only had to list 3. So these are all great ones to add, and this is something you might see on your test because this is a required lab for all students.